Okay. All right. Well, welcome everyone, and happy spring. This is Ibrahim Begeri. I'm a professor at the Faculty of Information at the University of Toronto here in Canada, and I have the pleasure of introducing our speaker today, Shiguang Wu, who received the SIGIR 2024 Best Paper Honorable Mention Award. Shiguang Wu is a graduate student at IR Lab at Shandong University, supervised by Professor Ren. He obtained his bachelor's degree from Taishan College of Shandong University in 2023. His research interests lie in information retrieval, particularly generative retrieval and embedding models. Thank you so much for joining us today and for presenting your excellent work, Shiguang, and the virtual floor is all yours.
Okay, thank you. Uh, Thanks, Professor Gregory, for the invitation and for CIGAR Forum for organizing this forum. And here I'd like to share our paper, which was published last year and also presented last year at the main conference. The title is The Generative Retrieval as Multivector Dense Retrieval. And this is a theoretical analysis paper and discuss a relationship between two models. And sorry, okay. So this is a joint work from Shandong University, Leiden University, and the University of Amsterdam. And I really thank for the co-authors for their fantastic contribution and hard work. So first, I'd like to introduce the retrieval system, which should be quite familiar with most of the people. And for a retrieval system, you first preload it with a large corpus, which is a bunch of documents. And when a user input a query, which is also a text form in this paper, and the retrieval system would return a list of document IDs that is things that are relevant to the user query. And normally, we will use a multi-stage retrieval system in industry. Like there is a retrieval and re-rank paradigm in a cassette way. And here we focus on the retrieval system. And it should be really efficient, and it is required to return hundreds or thousands of documents to preserve the high recall performance. And it really requires a very efficient way to design the retrieval system, and is different from the re-rank, which is more emphasized on the accuracy. And here I divide the retrieval system into three basic elements roughly. And this may not be very accurate, but here's the idea. And first, we will think about the scoring function, which is your theoretical modeling, how you modeling the relevance, how you compute the relevance between query and document. And it should be simple enough for a easy implementation, but it also have to be very expressive for the accuracy of the retrieval system. So first you have the scoring function. After you have it, we have to look at it and find which part of the scoring function can be pre-calculated and stored in the storage, so we don't have to recompute it again during online. And I think this is the indexing strategy, what indexing strategy doing. And we compute the document features like the term frequency or the vector representations of the document, and we compute that in advance and store them as a cache. And we also have to maintain a mapping from the feature and the ID, the exact documents, which features these features are belonging to. And so this is about the storage. And another important thing is the retrieval algorithm. So we have to do all this ranking in a very efficient way. So you have to considering the scoring and also the indexing to combine this and use them efficiently. Normally, we will want our algorithm to run in a sublinear time complexity. So we don't want to exhaustively iterate over all documents in the corpus. So we have to do some approximation to avoid that time complexity. So in order to propose a new retrieval system or new retrieval paradigm, we have to think about how we design each of these elements. We have to think them at once. So here are some realizations of a specific paradigm. So we can change the scoring function and indexing strategy to get a different retrieval paradigm. First is for BM25. We can use the term frequency, inverse document frequency, or the inverted index to build a highly efficient way to look up and pruning retrieval algorithm. That's for BM25 or sparse retrieval. That's quite common and basic retrieval paradigm. And another one is the bi-encoder model, which is the dense retrieval. The scoring function is much simpler. It models the relevance by the dot product between two vectors, the query vector and the document vector. So the indexing, what indexing doing is the storing to pre-compute the vectors and store these vectors. Or maybe you can use various quantization to optimize it. So this is the indexing. And for retrieval algorithm, there's a bunch of approximate nearest neighbor search algorithm, and for such as small world graph model. So if you have these three elements together, we can build the efficient dense retrieval paradigm, which is used quite a lot. And last is the cross-encoder model, which is one model accepts input of a query and a document. These two are input in the model together to get a score of the relevance. It's apparently more complex and time-consuming to gather score, and there's no easy way to pre-calculate anything. So there's no explicit indexing or retrieval algorithm. So it cannot be used for retrieval, and it can only be used in re-rank, which is much more complex and time-consuming way. So this is the overview of the retrieval system. And here I'd like to share the brief roadmap of our idea of this paper. So this is not presented last year at the conference. And first is the model-based information retrieval, or later it is called the generative retrieval model. It is first presented by Messler in 2021 and was published in the forum and as a blueprint. Like, they are thinking about so we have a lot of manually designed indexing or retrieval algorithms. These are highly manually designed in a very clever way. So this model-based information retrieval model is about we can build a fully learnable retrieval model. So we can let a big neural network to do all the stuff, to do all these three elements, like scoring function and indexing and the retrieval algorithms. We don't have to care anything about it. We don't have to design anything. So we let the model to decide how to design these three elements in a data-driven way. So this is a core idea. So it's quite popular idea to neuralize everything in a paradigm. So and our paper actually try to investigate what kind of scoring function is GR learning. So there has to be a scoring function. What is model? how does the model score the relevance? What it thinks these two, the query and documents are relevant. So at the very beginning of the GR was proposed, it is very difficult to distinguish between bi-encoder dense retrieval models at first glance, especially when using the atomic ID. So if you look at the implementation, you cannot say any difference between these two paradigms. So just like the dense retrieval, there are two vectors are making dot product and doing the retrieval. So there's no difference. So this idea actually come from the Shiguang at their paper Generative Retrieval as dense retrieval from the workshop SIGAR 2023, and they actually discuss about this equivalence, that a dense retrieval with flat index is just equivalent to GR with an atomic ID. So every document has a vector and a query has a vector too. So they're doing the dot product to predict the score. And so that's the atomic ID. What about the hierarchical ID? So a common implementation is to doing the hierarchical clustering to get the ID. So we're doing hierarchical clustering to get a string of tokens, string of cluster ID for this document. And this is, again, actually what tree index are doing. So another conclusion from their paper is that a GR model using hierarchical semantic ID is actually the same as a tree index for a single vector model. So they're actually doing a very rough discussion about this relationship, and this picture is also from their paper, and so what we can see from their conclusion is that we know that the decoding is actually what the component which performs the matching. So the encoder just provide the vector representation of the query, and all this matching are done by the decoder. This first observation you can get from their conclusion. And the second one is their paper fails to explain non-hierarchical IDs, and they didn't look at the internal mechanism in the decoder. They're looking at the top of the prediction head of the inference stage. So we can do much more by analyzing this decoder model. And again, the third one is they actually limited by single vector. Well, if you look at their conclusion, you may think that the GR model is actually not better, cannot be better than a single vector model. Like what this model doing is what is actually equivalent to a dense retrieval. So these are three observations from their conclusion, and so we can do some simple generalization. This is the very original idea of our paper. But they're comparing single vector models, and they're comparing the atomic ID. So what about the semantic ID? There's a simple generalization that we can use the multi-vector model, which is another very popular and supreme model used today in industry. And another thing is that we can, if we looking deeply into the model architecture, so we decompose what the attention, what the transformer are doing, we can get some more explicit, more useful answers to all these three problems. Like we know how decoder actually performs the matching, and we can explain all kinds of IDs, and we don't have to limit it by the single vector framework. We can find a relation with multi-vector frameworks. So this is the origin of our idea. And so next is the background of the paper. So so what is a multi-vector dense retrieval? It is first proposed by Omer in their paper Colbert. It's called the late interaction model. And for this model, we have some notation here. There is a document encoder and a query encoder. So before the document encoder, the documents are first projected to the embedding. So we call them the embedding vectors. And after the decoder, the documents are processed into a token vector. There's two notation here. And what this paradigm actually doing is the max-sim operation proposed by their paper, but every query token has to find the maximum similarity tokens in the document token. So and then we sum up these scores to get the final relevance score of the query and document. So this is the scoring function of their model. This is proposed, I think this 2020 a model. So there's a bunch of works of variant multi-vector dense retrieval, and this has very strong performance in the benchmark. So our paper actually also inspired by another paper from Google that called multi-vector retrieval as sparse alignment. They actually propose a very general framework that includes every multi-vector dense retrieval, also the single vector model. If we take the Colbert, the multi-vector, the Colbert as the example, the scoring function is the max-sim. We can actually decompose this equation into similarity and a maximum. So we split that into matrix. First, we can actually brute forcefully compute every similarity score for each pair of query token vector and the document token vectors. So we get a matrix of all the scores of the pairs, and we can also have another matrix called the alignment matrix, which computes which part of the pair, which pairs can be contributed to the final score. So actually, this is what their paper are proposing. That framework is a similarity matrix and an alignment matrix. So if this for the alignment matrix, it is 1 if the document token is the maxim of the query token, and 0 otherwise. So this is for Colbert, and we can actually generalize to a bunch of multi-vector model, and we can just adjusting the alignment matrix to get all these paradigms. So if we choose one element to be contributed to the score, so we got the dense retrieval, the single vector, and we can do similar thing to other paradigms. So this framework is very general and very strong. So next thing is about the GR, which is another important component in our paper. So here's a brief introduction of this paradigm. So given a query, which is a text form, it directly inputted in an autoregressive model, and this model directly generate the document ID. So it's just a end-to-end implementation of the retrieval system, as I mentioned at the beginning. So this is a fully end-to-end model, and we can just train this autoregressive model using the cross entropy loss, just like the sequence-to-sequence model. And we use the teacher forcing. So for the decoder part, we take the whole document as the input and shift one token to get the label of each position to compute the cross entropy loss. So during training, the decoder actually sees all the whole document. So this greatly simplify our analysis. And usually this autoregressive model is we use encoder-decoder transformer architecture like T5 or BART. And after train this model, we can use the constraint generation to get a valid document identifier. So we can know what document model are generating. So we are completing all the retrieval paradigm or the retrieval process. So here, let me look deeply into the model architecture of GR, which is actually the decoder part. As mentioned, the decoder is actually doing the matching. So if you down further, the cross attention, which is a critical part in the decoder, with this part is actually doing the interaction between query and document. So there's a self-attention, just the interaction of document itself. So the cross attention is actually the important component we care about. And so we do some simplification. We just look at the last cross attention layer. So that directly gives you the relevance score since it is a last layer. And we ignore the nonlinear activations in the feedforward network. So all these parts are linear, so we can directly use the output of the cross attention. So we can just ignore the FFN layer, feedforward network layer. So the final prediction head for the whole model is the output of the cross attention. So this is a cross attention mechanism that we have Q, K, and V for the attention. So the V and K here, the value and key are from the encoder, which is the query. And the Q, the query, there's a confusion of the notation here. The query for the attention is a document. So here's the how we compute the prediction head for the position I. So now we can think about the scoring function of these of GR. So we consider the prediction logits at each position as the relevance score. So we sum up these logits. So the EI here is the embedding for the document token, and if we plug in the prediction head here, we get this the equation on the right hand side. So firstly, we will compute Q and softmax. The softmax here is the attention score. So normally we will do that first, and then we will have a dot product with the embedding vector to get the logits of that position. So if we change the compute order, we first compute the embedding vector and the query vector, and then we do a element-wise multiplication with the softmax part. So we can actually get a very nice form. So the left part is doing the similarity matrix, and the right part, which is the attention score, we can view that as the alignment matrix as before. So we get these equivalents, and these two paradigms are equivalent set form, and the blue part is the document encoding, and the green part is the query encoding, and A is the alignment matrix. So we successfully generalize the GR into the framework, the multi-vector dense retrieval framework. So that's the main result of our paper. And so MVDR, the multi-vector dense retrieval, can be generalized into this framework, sparse alignment framework. The GR also compute this relevance using the same framework. So that's very nice result. So if we we compare these two paradigms using the framework, we have this two apparent difference. First, they compute the document encoding in a very different way. So the multi-vector, we using the token vector as the document encoding. So it is a contextualized. It contains the information from the context from the whole document. But for GR, it directly using the embedding vector, which does not contain any contextual information. So it's much more simpler. And we can think about the cross encoder, which we talked about at the very beginning. So it also use the very raw form of the document. It's just a text form and use that and input the raw form of the document. So from this perspective, and GR and Cobert and the cross encoder model are quite similar. And so the hard work is in the alignment matrix. So for MVDR, they use a very simple and sparse matrix. And for GR, they use a dense and learned alignment matrix, which is the attention mechanism. So so for GR, it uses very simple form of the document, but it do a very heavy computation during the online inference. And we think that alignment matrix is quite important for the computation. And we actually find first thing about this is the difference in alignment direction, which means that these two paradigms actually align in the opposite way. So for MVDR, if we look at the summation variable, iteration variable, it sum the score over the query token. So we call it the query to document alignment. So for each query token, it finds the most aligned query doc token to contribute to the final score. But for GR, it works in the opposite way. So so the score function here is sum over the doc token. So for each document token, it has to find the best match query token. So in this way, these two paradigms are quite different how they doing the alignment. We can have another view of the alignment direction. So this actually difference in how they do the normalization. So for MDR, they're doing the row-wise normalization, and for GR, they're doing the column-wise normalization. So this is the direction of the attention. But for MVDR, we actually find the max element in each row. So we can think about the alignment direction in this way. And there's a lot of experiments we done in our paper, and this one which we think is quite interesting, that we actually observe a similarity in how they do the alignment. So here we examine the soft-maxed alignment score, which is for GR is the attention score, and for MDR we add a use the softmaxed score. So these two paradigms have a larger alignment score for a rare token. So the token with higher IDF will have higher alignment score. So this is the one of the experiments in our paper. So there are other experiments, and think they're quite detailed. And so the experiment above is which we think is quite important. And so a summary of our paper is that we discover a new relation between multi-vector dense retrieval and GR in this neat form framework. So we have a lot of other experiments and discussion about low rank alignment, that the alignment matrix can be low ranked decomposed. So this decomposition allows us to develop a efficient way to the retrieval algorithm design. And we have some case studies in our paper. So here's the missing part of the paper. Like, we actually didn't study the effect of multi-layer interaction. So we just focus on one layer, one cross attention layer. So there may be much more complex mechanism for multi-layer interaction. And so another thing is that we study about the training stage. So it's much more simpler for us to analyze, because the decoder can see all the documents. But for inference, I think the inference stage is the highlight part in the GR. So it does a completely different way than all other paradigms. The inference just do the autoregressive generation. It can do the retrieval. So that's quite fascinating part. And here's the discussion from last year. We find the trend that multi-vector dense retrieval and GR are both quite popular paradigms this year. They're actually increasingly adopting very similar techniques. So we believe that this relationship can help researchers to build the bridge between these two area and develop more advanced paradigms. So unfortunately, this doesn't happen in this 2 years, and so we hope we can find something new in the next year. So here's a additional discussion that is not present in last year. On the right-hand side is a figure from a comment from Omar on the Twitter. It's posted in this year in January, and it says that he's the first author of the Colbert. So he thinks that what Colbert is doing is actually a hypernetwork indexing. So he thinks that for each document, we can construct a small DNN for each document. So, and for Colbert, we use the matrix form of the document and the matrix form of the query to develop a learned similarity function, which is the maxim function. So he thinks that the hypernetwork is a promising way to develop a very strong model. And there's another paper from Kuhnbeck in February. They actually use the hypernetwork for information retrieval. They use the hypernet for query encoding, the opposite component from Omer, and they rely on small word graph to do the efficient retrieval. So they're doing the hypernet for query, and so this is still not what Omar are thinking. So I think that maybe GR can be understood that as a hypernet for document encoding. And so during training, it learns a very complex similarity function, which is the multi-layer transformer decoder part are doing. So the document are provided in the text form, and the scoring function is constructed fully using the transformer. But for inference, so the training part is actually very similar to Colbert, and as we discussed in our paper. And so the critical problem is that how we develop a very efficient retrieval algorithm to do this hypernetwork at scale. So this is a very critical problem, and it's very hard to resolve. And I think for GR, it do it in a very strange way. So I think we for each document during the generation of the inference, for each document we have a prefix. What we generate for this document, we actually construct a specific scoring function for for all documents with the same prefix. So if we change the prefix of document of the input, we get a different scoring function. So this decoder is a DNN, is a hypernet for all documents. So for a document, we can see the cross attention layer. Like there are two inputs for the cross attention, the query encoding and document encoding, which we are generating. So if we fix the document as the input, as the parameter, and the query is actually the input for this function. So during generation, we are constructing the hypernet, which is the function of the query, and directly outputs the score for all documents with the same prefix. So I think that's a very interesting view for GR, and so I think it's quite promising for GR to be a hypernetwork. So there's no efficient way to for the hypernetwork for documents, and I think GR provides a possible way to do that. So here's a outlook for from our recent perspective. So we now have a initial framework for the scoring function. We can ask a series of questions. So first is about learning, how it is learned. So what is alignment metrics are learning. So how it gets during the training dynamic. And here's another paper in February called Cross Encoder Rediscovered a Semantic Variant of BM25. They studied the cross encoder and they find that the attention layer actually doing something very similar to BM25. So so they are using the interpretation of they're interpreting the cross encoder model and see something actually doing it for a very performant cross encoder model. So it's very inspiring from their paper. And so for the scoring function, we have a framework. And what about the retrieval algorithm? So there's another part, another element for a retrieval system. So maybe we can take inspiration from this fully learnable retrieval model, a dense retrieval, fully learnable retrieval model. And another question is a large generative retrieval model possible, just like LLMs? And we think that constraint generation, which was done during inference, it may be challenging to scale. We know that machine learning models are difficult at learning constraints. So we think that what restrict model from scaling is the constraints. So we have to use the constraint generation to make a valid document identifier. Or another way, maybe we don't have to constrain exact document identification. So we can change the retrieval system definition. So maybe once we remove that constraints, maybe the retrieval model can be at scale very easily. So this is my presentation. Thanks for listening.
Thanks so much, Shiguang. This was very, very interesting. Let me stop recording and then maybe we can go to questions.